ल हामीले रेकर्ड पनि गर्दैछौँ र यो रेकर्ड पछि उपलब्ध पनि हुनेछ है त वेलकम I'm Naveen Malakar acting as the vice president of ANPA we would like to welcome to the ANPA talk series discussing the 2023 Nobel Prize in Physics. This year's Nobel laureates in physics are Pierre Agostini, Ferenc Krausz, and Anne Lure. They have been recognized for their groundbreaking techniques shedding light on subatomic world of electrons. And Dr. Ghimire needs no introduction, but briefly, we are honored to have him as our esteemed guest. Dr. Ghimire, an alumnus of TU physics community and our dear friend of ANPA, is a very familiar face in our community. He obtained his PhD from Kansas State University in 2007, pursued postdoctoral research scientist at the University of Michigan until 2009, and subsequently joined SLAC National Accelerator Laboratory in the same year. Currently, he serves as the lead scientist and group leader at the Stanford Pulse Institute. Dr. Ghimire is also a recipient of prestigious Young Investigator Award from the U.S. Department of Energy for the years 2014 to 2019. Dr. Ghimire's research expertise lies in the realm of ultra-fast science with primary focus on developing innovative probes for quantum materials like two-dimensional crystals and topological insulators. A quick visit to his Google Scholar profile, you can see that he has a really impressive track record, about over 8,000 plus citations and H-index of 34. Without any further ado, let's welcome Dr. Ghimire. Dr. Ghimire, the floor is yours.
Thank you, Naveenji. Thank you so much, ANPA, for this wonderful opportunity, and also many thanks to NPS and all the members, my colleagues, my teachers, my students joining to this auspicious event today through WebEx. I'm really excited to tell you about the Nobel Prize in Physics of this year. And how what this actually means to us, to the physics community, and to the entire science community. This was awarded for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. And I will tell you today, what do they actually mean by attosecond pulses, and also what does it mean to study the electron dynamics in materials. Before I go on, I would like to tell you a little bit about myself, just to, Naveenji gave a nice introduction, but just a few punchline toward how I am qualified to tell you about this year's Nobel Prize in Physics. So this is in attosecond physics. So this is my career in attosecond physics, which started from my PhD work at Kansas State University, as Naveenji described. This is my group at the time. So I'm sitting there, younger me, and I'm actually next to my thesis advisor, Zhenggu Chang. And this picture actually tells me now a lot than at the time. For example, I'm sitting next to my advisor, right? And also, I'm actually on the right-hand side of him. He's a Chinese, advisor. So it means a lot. So I was, his right-hand person, and somebody he could trust me. So this is something now I can think of. At the time, I did not have any idea. After I finished my PhD in 2006, I went to University of Michigan, did a brief postdoc there, and then joined Stanford in 2009 at SLAC National Accelerator Laboratory. In 2014, as Naveenji mentioned, I received this wonderful award of 2.5 million, which allowed me to start my own group. Now, let me tell you a little bit about my advisor first, his qualifications. After, he taught us so many courses and guided us, the entire group, many people throughout his career in the research. He came out with this book, Fundamentals of Attosecond Optics. And at the same time, he came out with this shortest laser pulse record in 2012. He came out in the BBC News. His group, myself included, of course, were over the time able to show that the shortest light pulse can be generated down to 67 attoseconds. And we'll talk a lot about what this number means to us. After I left him, I started my own career, and this is where I am right now. So this is much more mature me on the right side. With a cover magazine that displays the work that my group did. Together with, on the left side, you see our paper where we co-authored with one of the Nobel laureates, Pierre Agostini. So he was one of my co-workers, senior advisor at the time in 2010. So this is how, I tell you, as I mentioned before, and I'm really extremely pleased to have my senior colleague Pierre Agostini as one of the awardees, and I know all the awardees, and especially Pierre is somebody I had lunch with, sat around table, and of course work with him. We actually went to his lab to do this experiment. Okay, so this is the day when these three Nobel laureates, Pierre Agostini from the Ohio State University, Ferenc Krausz from Max Planck at Garching in Germany, and Anne Hollier from Lund University in Sweden. They all received the phone call, right, from the academy, this is their picture as posted in the Washington Post, where the writer, one of the editors, Joel Arzbach, says that 3 scientists win Nobel Prize in physics for probing electrons. Okay, probing electrons. So that's the key. So why do we care about electrons, and how we probe electrons? So this is where the main meat of the talk is going to be about. So this is what the committee said: for experimental methods that generate attosecond pulses of light, okay, attosecond pulses of light for the study of electron dynamics in matter. So now first let us talk about what is attosecond. Okay, so it is the time, very, very short time. If you take a second and you divide by 1,000, it goes to millisecond, right? And divide by another 1,000, goes to microsecond, and then another 1,000 goes to nanosecond, picosecond, femtosecond, and finally it goes to attosecond. So 1 second is 1 attosecond is 10 to the minus 18 second. Okay, and to put this in the context, if we all know, right, our heartbeat occurs approximately once in a second. So if our heartbeat rate which is a second, is a good fraction, right, of the age of the universe, so whatever that fraction is, in the same way, the attosecond, 1 attosecond is the exact same fraction of the heartbeat. Okay, so 10 to the minus 18 second is the attosecond. So this is this very short time scale, and what is the what is there in this attosecond world? Okay, so as we talked about this briefly, we talked about the electrons, right? So this is just the schematic of a hydrogen atom which has 1 electron orbiting around the nucleus, right? So and this is just a classical description. Of course, in quantum mechanically, we never know where the electron is, right? But for the sake of argument, we can say that the classical electron goes around the nucleus, and the total time that it takes to go around is about 150 attosecond. Okay, so we can draw an analogy. So today we are having a solar eclipse, right now. It probably started. I should go outside. At least from our place, it is happening right now. And the the time that the Earth takes to go around the sun, right, is about to go completely around the sun is about 365 days, right? Because this time is given by the mass of these two bodies and the gravitational force between them and the distance between them. Just in the same way, the electron is attracted. Electron has negative charge, and the proton at the nucleus has positive charge. So there is a Coulomb interaction between this electron and proton, and just like the Earth goes around the sun, right? It takes 365 days. Here, the electron goes around the nucleus in the hydrogen atom, and it takes about 150 arcseconds. And it would be nice to measure this snapshot of this type of electron motion. And by the way, the atomic unit of the time is 24 arcseconds. Okay, so this is what now we know what the arcsecond time is, and what are the things that they move in this time scale. Now, why do we care, right? Why do we care about these electrons? It's those tiny particles moving around. Why do they care? Or do we care about them? There are many reasons. I will just give you two examples. On the left side here, you can see this this picture schematic of water molecule. So here, the water molecule, right, has the oxygen atom, and it is connected to two hydrogen atoms. And this connection between these two atoms is governed by the electrons. Okay, so the bonding between these atoms, for example, the covalent bonding between this oxygen and hydrogen atom is given by how these electrons are shared between the atom. If the sharing is different, like in other material or in other molecule, the bonding is different. So the chemistry, entire chemistry is different. So the electrons are glue, and they define the chemistry. That's why we care about electrons, because we care about the chemistry. We care about the chemical properties of materials. That's one reason. The other reason is that here, I don't know if you see my cursor. On the right, I have this picture of this transistor that everybody is familiar with. At least everyone in this call should be familiar with, should know how the transistor works, right? So it works at the fundamental level, how you turn around the current, the flow of electron, how you switch the flow of electrons, right? So we care. It would be nice to get handle on the flow of electrons externally, and maybe even without in a new ways, let's say, so we can have maybe faster electronics and things like that. So that's the other reason why we care about electrons. Okay, so it should be now pretty clear, right, why we care about electrons, just from these two examples, and what is the time scale of this electron. Now let's get to it. How do we produce short pulses of arcsecond duration? Okay, let's look at a little bit of history here. This plot shows the time scale on the x-axis and the pulse duration of the light pulses on the y-axis. So you might know, people who are working in the laser field would already know here, right? The beginning was really the discovery of the laser in the 60s. So the laser pulse, from the first one of the first lasers, were about this picosecond of duration. The pulse laser was a game changer, right? For example, when they discovered the pulse laser, not the continuous laser, the pulse laser was useful. So they sent the pulse laser, the pulse from the ruby laser, from the Earth to the moon. Okay, and then at the moon, the Apollo program had left the retroreflectors, mirrors, right? Retroreflector is 2 mirrors basically at 45 degrees, such that when you send the light there, it's gonna bounce back directly. So the pulse came back to the Earth, and that gave the measurement of the distance from the Earth to the moon with the accuracy of about a centimeter. So that's pretty powerful, all right? So that's just one example of the pulse laser. So in the history, the pulse duration went down and down. First with the mode locked, Q switch technique. For those who are from the laser field would know what it is. And then from this mode locking technique, so pulse duration went down to about few femtoseconds. Okay, to about few femtoseconds, because the most useful laser has been this so-called Tie-Sapphire laser, which has the wavelength around 800 nanometer. And this 800 nanometer corresponds to, in the time, about 2.6 femtosecond. Okay, when you make laser pulse shorter and shorter, right, you can, the limit, the fundamental limit is the length of this one cycle of the laser. You can't make it shorter than one cycle, right? Because you need a cycle to carry, you need a carrier to bring the pulse from one place to the other. So they were stuck at this, few cycle limit, about like a couple of femtoseconds. So that's where they got stuck. Now, this is where this Nobel Prize winning technology came in. So Anne came out with a new way, which is called the high order harmonic generation, which is a new way to produce X-ray pulses from this laser. Okay, X-ray pulses, because X-ray pulses would have much shorter wavelength, and therefore you could make a much shorter pulse. So that's the idea. Pierre Agostini went ahead and did the measurement in the time domain and found out that they were indeed a train of pulses, a train of attosecond pulses. Not one, but the train of attosecond pulses. And finally, Ferenc Krausz came out with a way to isolate one attosecond pulse from the train. So this is maybe a little too much, but we'll go through this in a step process. Okay, so first, let me just show you the result. This is the result that Pierre Agostini, this is the experimental data. So where they measured the pulse duration of such pulse. It's a train of attosecond pulses. Every pulse in the train is about 250 attosecond. Okay. And as I mentioned, then because of this short wavelength, they were able to bring the pulse duration really down to this 250 attosecond level at the time. So that was about at around 2001 and 2. So this is also the time, right, when I joined my my PhD. And our group started working on the same project, and eventually our group had the record in 2012 of 67 attoseconds. So this is actually after our group moved to University of Central Florida. And right now the record is from ETS. So they got the shortest pulse, 43 attosecond. This is the shortest human-made pulse of anything. Okay, so that's the Guinness book record. So it's 43 attosecond. So getting really close to the atomic unit of the time. So this is what led to the Nobel Prize, these three individuals. So let's go through this one by one. Okay, so now let's talk about what Anne did. The first experiment, so this is, as I mentioned earlier, it was to produce X-rays from the laser. Okay, so she did this in the form of the high order harmonic generation. So what she measured here is the harmonics of the laser to very high order, up to like 33rd harmonic of the laser. And it was surprising. So she shined in the laser just like it is shown on this experiment, because as I mentioned, right, I followed their work. So this is the work from my thesis, where I used the laser to produce high order harmonics. And in this experiment, I was able to produce, since this was 2006, right? And I was able to produce 2 times higher than what Anne did in the late 80s. But the experimental setup is almost exactly this. You focus the laser pulse into the gas target, and then you measure the high order harmonics in the propagation direction. This is one of these measured harmonics, right? So I had a better detector, I had better laser than hers, of course, you know, after decades, right? And my data looks much better. Of course, you know, either you be the first or be the best, right? So she did this first time, and I did better than that, but there were other people who you know recently did much better. So somebody were able to produce very recently up to 6,000 harmonic order. Okay, and this pulse, these X-rays are really like to 5 kilovolt range. So this is the technique, right, that allows you to change the frequency of the laser from the optical wavelength range, from the infrared wavelength range to the X-ray wavelength range. Because the X-ray wavelengths are so short, it allows you to make the pulses so short in time domain. Okay, now how does it really, like these harmonics, these are measured in the frequency domain. You know, how do you actually know that they support the short attosecond pulses? Let's talk about that a little bit. So this is the semi-classical model. It is called the recollision model, which describes the underlying microscopic mechanism of the harmonic generation process. So what you are seeing here is a very zoomed in picture at the single atom level and at the single cycle level. Okay, single atom of the gas and the single cycle of the laser. This yellowish curve is the single cycle of the laser, and this is the Coulomb potential of the electron. Okay, so when there is no field, for example, this is at the zero crossing. When there is no field, so this is the nice Coulomb potential, just 1/r, right? Everybody knows Coulomb potential of the electron. So when the electric field is imposed, like here at the peak of the field, this Coulomb potential is bent because this is you know, high electric field. You know, when you add a significant amount of electric field, you bend this potential in one way. Or, you know, you also suppress, right, the Coulomb barrier in that direction. And then what happens is that, you know, from quantum mechanics, we know, right, that if the barrier is suppressed, then the electron can tunnel out, right? So the electron can tunnel out, but for the general audience, you basically lower down the barriers, if you know, and then you know, you don't completely open the barrier, but you lower down and you basically pull the electron out of the atom. So that's the tunneling. So electron comes out. Now what happens? Remember, the laser is the cycle. So in the another half cycle, the laser turns around, right? When that happens, this electron first had been traveling in the laser field. Now it has to come back because the field got reversed. Okay, so this is basically Newton's mechanics, F equal to ma. Okay, so when the field reverses the direction, the electric field reverses the direction, the force on the electron is reversed, right, in its direction. Now the electron has to come back. So when it came back, you know, there is a small probability that the electron would come back at the same place where the parent ion was. When that happens, the electron could actually recombine to the parent. It's like, you know, sending your kid out to the college, right? You know, once in the winter break or summer break, you know, they come back to home. So when that happens, the parent ion is huge, 1,000 times heavier than the electron. The electron is super fast, right? Just like our kids, they're super fast. They do whatever they want to do. But when they come back home, we are not gonna move, right? The parents, we are 1,000 times. So what happens is that the electron has to lose that energy, right? The kid has to stay home, you know, nice and stable, eating dinner nicely with us, right? So when that happens, where does that all the energy go, right, of the kid? So all the energy of the electron has to go somewhere. So what happens is that it produces this very high frequency radiation. Okay, so this is what happens. And this is the third step. These are three steps, right? Tunneling, acceleration, and then recombination. So remember, the parent doesn't move. The electron was super fast, came back and smacked to the parent, and then it got recombined, just like going back to your house. and then the atom is, ion is finally back to the neutral state. The electron, all the energy that electron has acquired, which is given by this simple equation. This is basically how much the energy the electron can get depends on the laser parameters. For example, the strength of the electric field of the laser and the frequency of the laser. They depend quadratically. I mean, those are details. But so it can be up to kilovolt, right? That's how you produce the kilovolt energy. So there is almost no limit in this sense that, if you have the strong laser, right, or the longer wavelength laser, there is no limit on kids what they can achieve. Now, let's look at a slightly bigger picture. So this is how a typical laser pulse would look like, where you would have like several of these cycles. Okay, here I show like 3 or 4 cycles of the laser, and this happens every half cycle. So what you are seeing here is this at the peak of the field, for example, this electron came out, right, and then returned and went back to the same place. Okay, and then this is where it got recombined to the parent ion, and at this place there was one pulse coming out, one X-ray pulse coming out. Now the nice thing of this is that this recombination is coherent. Okay, so what coherent recombination means is that it will recombine to the exact wave function of the previous wave function of the electron. It would recombine to the exact electronic states, to, of course, to the exact atom, right? So when that happens, this window of the time that this radiation comes out is very short. So that's the key idea. Now the same thing happens the another half cycle, right? And then now you have so many these peaks of X-rays that are emitted at every half cycle. Okay, every half cycle. Now every half cycle in the time domain means if you Fourier transform this, right? In the frequency domain, they are separated by twice the laser frequency. That's why harmonics are separated by twice the laser frequency. It's pretty simple. T over 2, like half cycle, you do Fourier transform, you get 2 omega. So that's why the harmonics are separated by twice the frequency. Okay, so this is how you understand this figure. These are harmonics. They are separated, like, if you look at Enjolier's data, right? She measures like 7th harmonic, 9th harmonic, 11th harmonic, and the 13th, 15th, and so on. There is no even order harmonic. There's all odd harmonics. Okay, so hopefully this explains how these harmonics could support really short attosecond pulses. Now, how do they actually do the measurement? Okay, the measurement is not easy. So what they did was that Pierre Agostini came out with this method, which is called RABBIT. RABBIT stands for reconstruction of attosecond beating by interference of 2 photon transitions. So if this is complex, let's just assume this is an interferometry. So what he did was that he produced, right, the harmonics. So this is the interferometer. First, he starts with a laser. He splits the laser into 2 parts. One part, the reflected part, goes and produces the harmonics. They are shown here in this form, like XUV, extreme ultraviolet pulses. And they, and he takes this rest of the laser, and then he focuses these 2, both the laser and the harmonics, into another gas jet. Okay, into another gas jet, and that's where the photoionization occurs. What that means is that now this XUV does the photoionization together with the infrared, together with the laser, and they measure the photoelectron. And this the photoelectron, they measure the photoelectron, and they do this as a function of the delay between the laser, right, the one of the 2 arms, and the XUV. So this is the delay scan between the attosecond pulse train and the infrared laser from the other arm. So this is how the interferometry works at the very high level. Okay, and these are the citations if you wanted to know details about these measurements, and this is the result. Now, I was so intrigued at the time, And I wanted to do something like this exactly, right? And then this is what I built. So I started from around 2002 and 2006, when I finished my PhD. This is what I built. This is just the schematics. I started from a very similar laser like Pierre did, and then made the short pulse, and then made this interferometer and almost everything. And here, this portion is inside the vacuum. Okay, and this is where, without going into the details, you see this interferometry between this laser, which is in this pink color, and the X-ray. And there is this delay scan that we did, and so this is how very similar to what Pierre did. Okay. So that's how you measure at the very high level. That's how you measure this arrow-second pulses. Can you please mute yourself? There is a background coming from somebody. Thank you. Okay, that's better, right? Now, so this is how you measure these arrow-second pulses. Now let's talk about a little bit about what are the applications, right? What did they use these arrow-second pulses after all this hard work of doing this measurement? So there is lots of applications. Because of the limited time that we have, let me just tell you about one example experiment, which for physicists is a big deal. And this would give this would showcase the capabilities of the arrow-second pulses. So in this experiment, they took the train of these arrow-second pulses, as shown here in the green, and they did the photoionization of neon atom. Okay, neon atom is shown here. It has 10 electrons, right? And out of these 10 electrons, they took like 2 electrons out from the atom. 1 electron from the 2p shell, 2p state, and the another electron from the 2s state, both from the same shell. Okay, so remember Einstein, what did Einstein do, right? Photoionization. So according to the Einstein photoionization theory, you just like how things work in solar panel, right? You have the sunlight, and then you produce electron from the solar panel, right? And the electron goes into our house in the form of the current, and when we cook, right? Our heater works, and so it was assumed that this photoionization was an instantaneous process. Like you have the one photon going in, you produce electron, it happens instantaneously. So what this experiment showed is that there is a delay between these 2 electrons when they are coming out. Even when they were coming out from the same photon, one photon knocks down these 2 electrons from 2 different states. And when they measure the electron coming from the 2p and 2s states, they were actually delayed by a little over 20 attosecond. Okay, so the electron from the 2p state comes a little more than 20 attosecond ahead of the 2s state. So such a precision measurement was possible because of the use of these attosecond pulses. Okay, now you might ask, maybe you already have question. You could, I don't know, I guess you could put it in the chat or hold on to those questions toward the end. So you could ask, then what's the limit, right? So there is the Heisenberg uncertainty principle. If you know this, position, you may not know the energy and such. So here the precision is determined by this interferometer precision. So how good you can move the laser arm with respect to the X-ray arm. So that's the limit. And you can, of course, do down to a couple of attoseconds with the current technology. Okay, so let's leave that there. And then now let's talk about, right? So this is all done, right? So we are here to learn about what happened, and then what's the next thing, right? So what is on the plate, and what is the impact in the field, and if there is a like I assume we have lots of young students trying to find their PhD projects and things like that. So what is next? So let me just tell you just a couple of things about the challenges of this technology. So this entire array-second, almost entire array-second technology is based on these gaseous materials, like atoms and molecules in the gas phase. So this is the picture, right, of of high order harmonic generation, this three-step model. So this is in a more concise form. So this has to occur inside one atom, right? Now the question to you, to the audience, I don't know how do I get the answers, is that when this electron went out and came back, right? So what do you think is the probability of this electron finding the exact same parent ion? So what is the probability out of, let's say, 1 out of 10, 1 out of 100? I mean, kind of like when the kid comes back to your house, so what is the chances that he will find your house? Probably, almost 100%, right? But so what is the probability of this electron to find the parent ion? Because electrons, they go everywhere, right? In the macroscopic scale. So make a guess and put it somewhere in the chat. I don't know, maybe in the Facebook. What is the probability of the electron finding the same parent ion, like 1 out of, if it is 10 or 100 or whatever it is? Make a guess and put it down. And I will tell you the result. You just have to get the ballpark right. Okay, I start seeing some, okay, there is a, okay, 10 to the minus, so probably it's supposed to be -6, right? Okay, I see one answer. So that I just said 1 out of a million. So that's pretty good. Okay, so there is the half, okay, 1 out of a million. Oh, now there's lots of answers. Okay, I like it. 10 out of 10, come on. That's for the kid to find their parents' house if they are not drunk, right? Okay, so it's like 1 out of like a million. So what that means is that the light, the amount of light that we are talking about is actually very minimum. So when you have like only 1 electron out of the million electron, producing this light successfully, think about the efficiency. It's lower than million. So for the laser, like if you have a million photon of the laser, you'll get only 1 photon approximately. So that's not efficient, right? So also when you have this already low efficiency light, and it's really hard to deliver this light to materials for materials study. So this was really really the inspiring deficiency for me. And then I started thinking about increasing this recombination probability. So I wanted to do this in crystals, in solids, because solids have high density. So when the electrons come back inside the solid, right, there is a pretty good chance that the electron would hit the parent ion, if not on its own parent, it's somebody else's parent. When you have the high density in the neighborhood, right? So electron, the kid will go to somebody's house for sure. So it's just like that. So if in crystals, these atomic sites are actually coherently connected, the wave function is delocalized everywhere. So doesn't matter whether you go to your own house or somebody else's house. Okay, so you'll produce harmonics coherently, and we at the time I did not know this. That's why I did the experiment, but it's been like 15 years after the experiment, now we know it is true. Okay, let me show you some results from that experiment. So this was a pretty cute experiment. We started with the mid-IR laser pulse. Also, this is the experiment that I did together with Pierre, one of our Nobel laureates. So we took the laser, we focused the laser pulse into a zinc oxide crystal. There's a number of reasons why zinc oxide, but I guess we probably do not go to those details today, some of the time. So we, just like in N. Hulier's gas phase experiment, but in solid, so we measure harmonics there. Okay, so here we see, where's my cursor? Right there. So here we see high order harmonic spectrum. You always measure the limited range because you know of the limitation on your spectrometer. So you can see here the harmonics from 9th order, right, to 11th, 13th, 15th, 17th, and when you increase the laser intensity, you can see up to like 25th harmonic. Okay, and Hullier measured up to 33rd, so I was pretty close, you know, 25th harmonic from solid. Okay, and the nice thing of the solid is that it's a crystal. You can rotate the crystal and see what happens. So this is the experiment. When I rotated the crystal, so in addition to these odd order harmonics, I also measured this even order harmonic in certain orientation. So there is a very interesting activities inside the crystal that is going on, you know, in terms of this, how these electrons are driven inside the solid material. The other thing I noticed was that this high energy cutoff, so that means, you know, the highest energy cutoff has this arrow, you know, pointed here. So this actually scaled very differently than in the atoms and then in the gas phase. Okay, there were some differences, and therefore we wanted to know, right, what is the mechanism. And there is lots of activities in the field about this, you know, solid state high harmonic generation process. There are many groups working on this, and there has been also a debate, significant debate, so many nature and science papers on this topic, but it's more or less settled. So this is how it occurs. Okay, so now I'm wearing the hat of condensed matter physicist. Okay, so this is the simple schematic of the band structure. So here you have the valence band, okay, on the bottom, and there is the conduction band. Originally, the valence band is completely filled, like in any other semiconductors or insulators. The conduction band is completely empty. With the help of the laser, there is some electrons from the valence band, they tunnel to the conduction band. Okay, just like, you know, how the tunneling works in the you know, Zener diode. it's the same tunneling. Okay, because there is a sufficient electric field to push the electron from one band to the other. It's pretty simple. Okay, it's like the almost DC like field. Now you have these electrons in the conduction band, which is partially filled. Now we have only few electrons. Okay, so they are now driven in this conduction band, right, very rapidly, because the laser changes the sign. It goes like blue, 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 right, back and forth, and maybe even faster than in the gas, because this is a periodic system. So when this happens, this electron at some point could recombine to the parent whole, just like in the atomic case. And this difference energy, so this is my three-step model: tunneling, right, number one. Number two, band acceleration. Not only the electron, but also the hole, they get accelerated in the momentum space by the field. And at some point, this electron would recombine, and the difference energy, right, to the hole, and this electron and hole's difference energy comes out in the form of this high energy X-ray photon. Okay, so when you have this X-rays or high energy photons coming out from the material where the electrons were you know, driven in the material, right, and following the electronic band structure, they can't go randomly anywhere, right? It is like the very well-defined highway. So there's different lanes. Lanes are bands. There are forbidden gaps, right? You can't go, you know, just like in the two-way traffic. So what that means is that in the material systems, the electrons have to follow both the electric field and the electronic band structure. So this is actually a good news, because when the light that comes out, then it might have the imprints of what happened in the production mode. right? So just like in the, if you know, you're crossing the bridge, I have to cross the bridge every day. So when there is a traffic, right? So I come home like 1 hour, 2 hour late. Okay. When there's no traffic, I come in 30 minutes. So just like that. So when there is a certain band structure that has certain type of dispersion, you take some more time to move there, for example, then the light that comes out may be delayed, right, in the phase. So you can measure that. So this is just one example of how the light that comes out from the solid could be used to measure these very fast processes that are occurring inside the solid. Okay, now I would argue that I solved, right, at least tried to solve two problems together. The first problem was to produce enough light, right, because it's solid. Now the second problem was that it was hard to deliver the attosecond light to the materials. Now we are producing inside the material itself. Okay, so this is the basic idea at very high level. Okay, and now we're almost toward the end. I think I have about 5 minutes. So I will just show you one example of the use of this, harmonics in materials. So this could be interesting for students working or trying to find interesting material science problems. This is the what you see on the top is the electronic band structure, measured electronic band structure using a different method. Okay, very standard method. And this material is a topological insulator, bismuth selenide. And, this is what, how they got the Nobel Prize on this, right, many years ago. When you add impurity on this material, so you change the topology. Okay, so this is the band structure. The topology is seen here on this Dirac cone. Okay, this is like graphene. If you just look at the cone, so the crossing of these bands is what we mean by the cone, crossing of the valence and conduction band at one place in the momentum space on the surface. So this is the band structure, and when you add in more impurities, this cone disappears. So this was already known, right? Where you put in this X-ray photon and you measure the electron. That's how you do this measurement. What we did is we use the harmonics. Okay, this is our setup. We signed our sample with our laser. In our case, the photon energy is much smaller than the band gap of the system. Therefore, there is no photoionization in that sense. Okay, so there is not enough photon energy to get the electron out. But what we do is we get the harmonics out, high order harmonics out. And in this measurement, what we are doing is we're changing the polarization of the harmonics, the polarization of the laser from linear to circular. And what we found out is that from these two extremes, so this extreme is the topological material. Okay, this is topologically non-trivial material. This is topologically trivial material. Trivial meaning that there is no Dirac cone here. Okay, so there is a very different, qualitatively different emission profile of harmonics from these two materials, two phases of the same material. In one case, the harmonics intensity increases as you change the laser from linear to circular polarization. In the other case, the harmonic intensity decreases when you change from linear to circular polarization. This is very different. Okay. Also, remember that in the gas phase, the electron had to come back exactly, right? And that's why you only produce harmonics for the linear polarization. If it is a circular field, the electron goes in helix like this. It would never come back to the same place. Okay, it would go forever. But in solid material, it doesn't need to come back exactly to the same parent ion, right? There is always ion, everywhere. So even for the circular field, especially in the topologically protected surface states, this emission seems very efficient for circular polarization. So this was one thing is that very new, is a clearly new discovery in the high harmonic generation process itself, because circularly polarized lasers would not produce harmonics otherwise. And this is a potentially new way to probe the materials. And there are many examples, many other examples that our group and other many groups are working on to use the harmonics as a spectroscopic tool. Okay, this was if you want to know more about this work, you can go to our paper, which appeared in Nature Photonics recently, meaning that, last year, 2022. So that's just the one example. So toward the end, I have 1 minute. Toward the end, let me just tell you what I think is the roadmap of this this high harmonic spectroscopy. Okay, so we started in the community. We started from atoms and molecules, like from really from N. Hullier's experiment in the 1987, right? So the one of the Nobel laureates, when she observed the harmonics from the atomic gases in the argon gas. From there, the field started. Field grew from atoms to molecules, and then in the molecule, I didn't get time to talk about molecules. So when this electron, right, the driven electron was coming back, right, depending on the shape of the molecule, because molecules are not isotropic like atoms. Molecules have like interesting, right, orbitals with geometric shapes. What you see is just a simple diatomic nitrogen molecule. So depending on how the molecule is oriented, when the electron comes back, it sees the different portion of the wave function, and the recombination efficiency is different. Therefore, what you measure is the intensity of the harmonics depending on the angle of the molecule is very different, and they use that information to basically reconstruct the electronic wave function of the HOMO orbital of the nitrogen atom for the first time in 2000, around 2000. Okay, it is kind of like the molecule is sending this electron, and on the way back, like it's like taking the selfie. Okay, if you are facing this way or this way, right, you look different. Like the molecule, right? If the electron was hitting this way or coming from this way, so that's how they took that's the basic idea. Okay, they took the they took the picture of the molecule. So from there, we extended this technology to solid materials. I told you about our first experiment that appeared in around 2010, which we actually shared with another Nobel laureate, Pierre Agostini was one of the co-authors. And since then, there has been a lot of activities in this field, particularly in condensed matter systems. And relatively recently, several groups are working on topological materials, 2D crystals. These are quantum materials, right? And not a lot of things are known, but there's lots of potential toward like interesting applications in quantum, in the quantum technology. So this could lead to, right, I draw until up to around 2030. I mean, this is a good time scale for another PhD, like, which would take like 5 to 6 years, right? So we're in 2023, so if you're interested, this is, I think this is one of the possibilities where, you could combine strong laser fields to materials and then come up with a new ways, even the new type of electronic band structure. For example, in some correlated material systems, the applied electric field can significantly change the electronic band structure, but there was no good way to measure the band structure. So harmonics could be optical method to probe this band structure. So that's how I think the field will evolve, and this has been very exciting, of course, because of the Nobel Prize, and I think it will essentially the field will grow, and personally I would think that it would be great if we can contribute, from both from the AMO to like to material science community and to laser technology community, and just basically bring together people, including from biology, bring together to to the table with various type of capabilities and possibly do applications. This is my last slide. I would like to thank my wonderful colleagues. These are my recent colleagues that I work with. The top row is my colleagues at Stanford. They are in-house. The Yuki Kobayashi is my latest postdoc. He finished with me, and he is starting as a assistant professor at University of Michigan as I speak. This semester. Christian Haida is another postdoc. He is in the lookout for faculty positions. Denitsa Vakisheva is also my former postdoc. She is starting her faculty position this year as I speak. And Feng Lu, Tony Hines, and David Rees, these are my senior members. They are faculty at Stanford. On the bottom row is my wonderful colleagues from outside Stanford. On the left is together Ludi Maro and Pierre Agostini, from the Ohio State, now popular Ohio State. Their first Nobel Prize, okay, I think, in the university. And Mera Gard, she's a theorist from LSU. We worked with her on many collaborative experiments. Alexei Sakon is in Korea, MPQ, also theorist. And finally, there is a Brodger group who is doing really nice MBE, using MBE techniques to grow topological insulators. And with that, I would like to thank you very much for your attention, and I would be happy to take the discussion, take your questions or comments. And once again, thank you so much, ANPA and NPS, for this wonderful opportunity. I hope it wasn't boring.
Thank you, Dr. Ghimire, for this wonderful and informative talk. And looks it should be the most burning topic at this moment. So we'll take a few questions for Dr. Ghimire. So I will start from the chat box. I see a question from Suresh Ghimire. So Shambhu sir, you want me to read the question or you can read yourself?
Yeah, please go ahead and read it, because I don't see the chat box on my side. They were popping out. But,
sure, I can read it for you.
Yeah.
So Suresh Ghimire is asking, what is the physics behind changing harmonic intensity from circular to linear in your experiment?
So the first, let me tell you about in Hulier's experiment. So in her experiment, when she changed from linear polarization to circular, she saw nothing, right? Because in the atomic case, when it is circular field, the electron doesn't come back exactly to the atom. Now in my experiment, especially in topological insulators, the circular is actually stronger than the linear because of the selection rule. So here the generation is mostly on the surface. The surface, as I said, is topologically protected surface. And what that means is that it can support either a spin up or a spin down, one of these two. And there is theoretically no resistance to this driven electron in the circular field. So especially if you couple left circular or right circular field, you selectively drive these electrons, either a spin up electron or the spin down electron, without resistance. In theory, there is no resistance on these surface electrons. So when you can go crazy with no resistance, right? And it produces lots of light. So that's the very high level explanation of why the generation in circular polarization is much more efficient in the topological insulators. I hope that explains.
Another question from Pravesh. He's asking, why do we need to use IR laser to generate HSG?
Because you have to take the electron out. Okay, so this was also the key. So you needed high power laser to knock out the electron, in the first place in the gas case, in the gas phase. And it turned out that in solids, you don't need that much of high power, because in solid, you don't really need to get the electron out from the solid. And also there is high density. So in solid, actually, we use, compared to Enholier's experiment, we use like 2-3 orders lower, the intensity of the laser. So in the gas phase, you needed that high intensity because you needed to get the electron out from the atom.
I don't see any more questions in chat box, so everyone, please feel free to unmute your microphone and raise your question.
Okay, so there's a Provis
Hi,
has.
can I answer? Oh, sorry.
Let me answer.
Yeah, I see one question from Provis. Following question, maybe.
Yeah, this question is important because before Enholier's first demonstration, right? So which was using the infrared laser to produce these high order harmonics. Before that, people were using high intensity lasers to look at the harmonics, but they did not measure, this very high order harmonic. The reason was that they did not use the long wavelength infrared laser. They actually used the visible, like excimer lasers. At the time, those are the intense, laser sources. So they use the relatively lower, short wavelength lasers. So even though the electron was, pulled out, or like it's not even pulling out. Let's say if you have the intense UV pulse, you can photo excite. The electron does come out from the atom, but because the wavelength of the laser is so short, right? This electron trajectory that we talked about is very small. So the electron doesn't really acquire enough kinetic energy from the laser pulse, so it can produce high order harmonics. And it's like, you send the kid out from the house, but you don't let him drive, right? How far it can go. So it's just like that for the short wavelength visible excitation. And although you can excite the atom and produce electron, the electron doesn't really go far enough to acquire enough kinetic energy, so it can give high order harmonics. That's a very good question.
Question from Sunil Karki. So what are the orientation to observe second order harmonics?
So the orientations, so it's pretty simple. So if there is an orientation where you break the reflection, the inversion symmetry, if there is a inversion symmetry is broken, right? So in atoms are spherical. So if you look at if you are at the center of the atom, you look at the left side or right side, it looks the same, right? But in crystals, depending on the orientation, if you're sitting inside in the unit cell, let's say if you're sitting at one of the atom, and if you look at the left or right, if they look the same, so let's say that's the inversion symmetric system, then you cancel the even orders, so you only produce odd order harmonics. But if the system does not have the inversion symmetry, left and right look different, right? Then both produce harmonics, and there is no cancellation. So that's the reason why you actually observe even order harmonics in solid materials. But in the gas, like in the atomic and molecular systems, you only observe the odd harmonics. So it's just the inversion symmetry case. So remember, lasers are always inversion symmetry in the multi pulse limit. So if in the laser, the up and down is the same, right? So as long as laser doesn't break the symmetry, when the materials break symmetry, they produce the you see the even order harmonics.
There is another question from Rudra Kafle. So he's asking, is this analogous to brainstorming in some sense? The only difference is the energy scale.
Yes, that's a very good question. So not the energy scale, okay? The difference is the coherence. So brainstorming can be very high energy. So that's how, like this in the synchrotron radiation, for example, you get very high energy radiation. It can be very high. It can be, tens of kilovolts or more, but it cannot be coherent. So that's the difference. So to emphasize, to make it clear to students, right? So you have a light bulb, it can be very bright, but it's not coherent, right? It's not a laser. So laser has both the direction, right? The it has a direction, and it is coherent. It has the other properties also. So the harmonic generation is a coherent process, but the Bremsstrahlung is the radiation just from the electron, right? It doesn't return. So even when the electron would return, you in some cases, you measure the fluorescence light, right? So fluorescence emission, that's the emission from the atom, but it's not coherent. It's an incoherent process. So that's the key. So the harmonic generation process is a coherent process. So because it's a coherent process, it allows you to take the picture of the wave function of the electron, right? Because it's the same. You split just like you split the pulse by the interferometer into two, right? And you can measure this pulse by bringing them together. So just like that, in the harmonic generation process, you split the wave function of the electron into two. One goes out, and the other stays in the atom. And when it comes back, it finds the exact same, this another half of the wave function and recombines, right? And it produces harmonics. So this is the strength. So if it was not a coherent process, then you had no idea. You could not image. You could not use this for imaging. Thank you.
Neeraj, you said you have some question you want to ask yourself, right?
Yeah.
Please go ahead and.
Hi. Hi. Very nice talk. Thank you for a wonderful talk, Dr. Ghimire. So I am little confused about how attosecond pulses are used to probe the materials. So as far as I know, in the femtosecond community, what they do is they generate the pulse outside the material, and then they sign in the pulse to probe the band structure or the response of the system. So is the same thing done here, or it looks like you are also generating the pulse on the fly in the material? Did I understand it correctly?
Yeah. So right. So that's the basic idea. So conventionally, maybe it helps if I unshare the screen.
Yeah, exactly.
How do I unshare? Here, stop sharing there. Hopefully I didn't kill it. Okay. Right. So in the solid state harmonic generation process, you actually produce harmonics from the solid itself, right? So the idea is that if you understand the generation mechanism, inside the solid, then all you need to do is just measure the light that comes out from the solid. You could measure the polarization of the light. You could measure the phase of the light, perhaps the spectral phase of the light, and learn about the electron activities that is occurring in the material. You can think about probing the electronic band structure by measuring the harmonics. In fact, there has been already some work in that direction. So that's the idea. The idea is to produce harmonics inside the material itself. As you can certainly do that in crystals like the insulators and semiconductors, and actually it turns out that even in metals, right, you can produce harmonics in using the reflection geometry, as I showed in the topological insulators. So that is the idea, that you don't need to deliver the harmonics to the material itself, but it depends on on what you want to measure. I mean, there's always a possibility to take the light and use it on materials where you could have a different type of control, like photon energy of the light, for example, and things like that.
So it is in a way indirect measurement of the band structure of the material in a way, right? So for example, in the ultra fast femtosecond community, they probe the light itself, and then they see how the electrons are transitioning to the higher states, right?
Right.
So here it's indirect, but of course powerful technique.
Right. Yes,
okay.
absolutely.
Thank you.
Yeah, here we need to develop the understanding of the generation process, right? Which is the fun part.
Thanks. Great talk.
I have a question.
Sir, well, okay, for everybody, we will take the questions from chat box first, then we'll go like live questions. Okay, so Shambhu, I think you can read now the chat box, right? So there is question from Sriram and Tikaram Kaple.
So how do
I can read it if you want me to do that.
Yeah, please start reading. I will try to find the chat box here.
It should be all the way in the right, left, right
I see.
bottom corner.
Yeah, I see it now. Okay, so you can start, and then I would find out where we are. Yeah, on the list.
Yeah, it's from Sriram. He's asking, you mentioned the electrical aspect of electromagnetic radiation to rationalize effects. Does that mean that the magnetic aspect of incident radiation is significantly weaker?
Yeah, that's a good question. So for the moment, it's very weak by orders of magnitude. But when the intensity of the laser, is really high, right? Then you need to consider the magnetic field. For now, it's only the electric field. The magnetic field is because the effectively there is you need to have like several orders higher magnetic field than they currently have. So right now it's only the electric field. The magnetic field is insignificant.
Yeah, just a follow-up, Shambhu sir. So, but still on the output, you still see the magnetic effect, right? Is that quantized? Is measured on that result side or not?
So what do you mean by the magnetic effect?
Is any result is measured, I mean, or rationalized in terms of the spin up or spin down? Because in somewhere you mentioned the spin up, spin down. Still
Right.
on the measurement side, there is that resolution, but on the when you consider the incoming radiation, still the whole effect is from the electrical path.
That's right. So it's the mainly the electric dipole selection rules are dictating, right, this the emission from certain spin polarization. So there is no magnetic effect. It's just the orbital angular momentum conservation to either to like spin up or spin down. But there is certainly interest, right, on a slightly different way. Maybe you can use this magnetic properties not of the light but of the materials. So there is actually some activities there. So magnetic properties of the materials, can respond to the light in a way that could be really insightful. So actually, we're doing next set of experiments on magnetic topological materials where we might see something really interesting.
Thank you.
From Tika Kaple, how does the line width and pulse width scale with increasing order of harmonics in solid state HHG?
Yeah, so of course, right. So when you want to have the really short pulse in the time domain, you need to have a really large bandwidth in the energy or frequency domain, right? So the harmonics are already so wide, like in terms of the bandwidth. So we are talking about, even from solids, like 50th, harmonics up to about 50th harmonics. So that's a huge bandwidth. The problem is there are no good optical components like mirrors and things like that to take the entire bandwidth. So you're basically limited by the optics, to use. But yeah, so in principle, if you are not limited by the optics, then let's say if you produce harmonics from solid and then you want to measure, right, the pulse duration, if you can focus all the harmonics for that measurement, to that measurement device, let's say, then you could potentially get really short pulse. And in fact, that is the limit for the current, what did I say, 42 attoseconds, right? So it's not the bandwidth of the light that is not there. It's really the optics that they use, have the limitation on the bandwidth.
Okay, thank you so much, sir.
Any more questions in chat box? So if anybody have any question, please feel free to unmute
That's a good one.
and raise
What
your
are
hand.
your advice for undergraduate physics student? So the it's a new field, and I think if you like optics and lasers, so I actually describe this to undergraduate students. They seem to understand it well. So my advice is to try to read some of these popular papers, like from Nobel Prize winners, some documentations, and see if you find anything interesting, right? And usually go to like popular articles which are easier to understand and will help to draw your interest to a certain field. So instead of like focusing on one physics paper, I would suggest to read a general like science magazine or general paper, and which are easy to understand, and it can be useful to draw your attention to a certain field.
Yeah, hand raised by Dr. Vishwanath sir. So Vishwanath sir, you can unmute your microphone and ask your question.
Okay, yeah. Thank you, Shambhu. Very nice overview of the field. It's good to hear that AMO got the prize this year. I wanted to ask a different question, not about the physics, but I mean the ones that got the Nobel Prize are like renowned. But do you think someone is excluded in the community?
Well, they have the limitation of 3 people, right? You can't give the prize to more than 3 people. And the first thing I thought was when I saw the names, right, of people like since these names, right?
Yeah, that's right. That's why, like, I wanted to ask, like, what is the
Yeah. So there
thought
is
from the community? Was there any reaction? That's what I wanted to know. Like.
Yeah, I think there is some activities in the social media about for example, why it did not consider Paul Corkum. That's one, right? And I think it's just the limit that it has 3. you can only give to 3 people, and also the committee probably wants to survive, and they're looking at the diversity, and they gave probably the giving the prize to Enolier was probably in their mind, including diversity, and she's the just the 5th Nobel laureate, 5th female Nobel laureate. So
Yeah, but like, do that's why they put the electron dynamics in the remarks, or like how it's a very tough choice, right?
yeah,
Like,
it's very
personally, what
difficult.
do you think? Like, did they go beyond like general and make it very specific, or like it's kind of unsure, like what criteria would exclude someone very close to the others?
Yeah, absolutely. Yeah, I don't know. That's the right answer.
Yeah, I just wanted to know, like is it just like, obviously there is some feeling within the community that it's not.
Right. Yeah, but I guess we have this feeling now, right? Because it is in our community. But I'm sure this is the same feeling that everybody has in their community when they get the Nobel Prize, because it's limited to like 2 3 people, right?
Okay, yeah, that's good to hear. Thanks.
From Sunil Karki, Shambhu sir.
Okay, so let's see. I'm supposed to read, right? What motivate you do a lot of this type of research? Can you share some things to us? Thank you. So the motivation was, okay, so let me tell you the initial motivation. So when I was a PhD student, I went to my advisor, right, and then asked him a very simple question. So what is my PhD project? It was pretty simple question, and he gave the blunt and simple answer. Shambhu, you produce the shortest pulse and measure it. That's exactly what he said, and he was absolutely right, right? And now, like much later, now I realize that, oh wow, this is what he was talking about. It's a Nobel Prize winning thing, right? So, but it was very motivating. Oh yeah, you can actually measure the produce the shortest pulse that in the humankind and do that measurement. So that was the initial motivation. And then when I work on my thesis, I was very closely working also with Bishwanath's advisor at the time in their group, right? So I was really amazed by how well this recollision mechanism actually works, right? So I wanted to find the limitations of this, and how this is so well, how it works so well, this coherent recombination thing, right? What happens if you have like multiple sites, right? So that was the something really was inspiring in some sense to understand the limitation, and that was the reason to try the solid, like the crystals, right? So that was the turning point. Actually, it turned out to be good. I mean, I had to teach myself solid state physics, because I never had a course. So it was a complete switch, but it was a good thing that I was able to learn a completely new field. So I think the mainly two things, the inspiration during my PhD was, wow, as a student you can do this things like producing the shortest light pulse, right? And later, so when I switched the field to condensed matter physics, it was also inspiring because, oh, you can do in solids, right, from condensed matter physics communities. So yeah, thank you so much. And the next things on my line is using X-ray free electron lasers. So that's the next, possibly next big thing in the community, to produce and use the attosecond pulses from X-ray free electron lasers. We have one of those here at Slack. Okay, so let's read.
Guy has question again.
As an undergraduate physics student, I'm interested in research, but I'm quite lost on what topic should I start with. Yeah, that sounds familiar, right? You have suggestions for doing research as an undergraduate with no experience from scratch. So as an undergraduate, a lot of these activities could sound like pretty complex. But I think at the conceptual level, once you understand things, a lot of things are actually pretty simple. For example, the semi-classical model, right? So as Bishwanath, for example, knows that in their group, they used to have lots of undergraduate students, and they understood. So once you get hooked up to certain research groups, they can break it down for you, right? So it's especially the optics part of it, I think is very easy to break it down to the level of undergraduate and even to the high school, I would say. Yeah, hopefully that answers at least partially, partially about the undergraduate. So I would add that at Stanford we have really nice, undergraduate, what do they call, the summer program. So if you are interested, you could apply. Every summer we take, I think like 30, 40 students. They come here paid, like, on, summer intern. There are lots of opportunities. So these opportunities, would give you like it's there for a short time, but give you, you can visit different research groups and get some experience, and hopefully you'll find something that draws your attention for your career. Okay, so let's see, the chat moves. Okay, Bipin Bandari, and if possible, please somebody give us this sort of talk on how to start doing research as an undergraduate. Yeah, so this is probably a good question for ANPA. Okay, ANPA.
Yeah, first of all, like I would say, we have a session on AWW in December, and where like students from like different stage of their career as a researcher, that might be helpful for you guys. And other thing I would say, go to our website, you'll see so many mentors from our group, and you can choose one of them based on your research. Then you can try to reach them out, and you can start from there. Or if you have any questions, just shoot us an email, and we will find somebody who can help you in your area of interest. Yeah, please keep tuning, then we will have something. It's ongoing process, and as I said, always feel free to shoot an email if you have any specific interest or something related to physics. We'll try to resolve it. Thank you. So, any other questions from anyone from audience? That's no question.
Yeah, I don't have particular
go ahead, Dipesh.
question, but if you have a time, I would like to continue my,
Dipesh, I
my-
request you to continue that after the formal session. Let's
okay.
let's focus on the talk today. Then probably we can do that later.
So I expect some questions
Oh, yeah.
from people joining from Nepal.
Hoping so. Also expecting so. People in Nepal mostly do like simulation and computational. That's why they might have more questions to ask that. So meanwhile, one question. I have a question, Shambhu sir.
Yeah.
So as physics said, like when you go like higher and higher harmonics, you keep losing energy. Is that true for like all kinds of lasers or what?
Oh yeah. So let's see if I can, and maybe I'll just describe. So when you look at the harmonic spectrum, right, which is the intensity of the harmonic as a function of the energy. So first you see that as you increase the harmonic order, the intensity goes down, and then you reach a plateau where the intensity stays the same for many, many harmonic orders, and then you reach to the cutoff. So so that's the basic characteristic. And now the reason why the intensity of the high orders, much higher order, is lower is basically you need to drive electron to high kinetic energy, right? And usually the total when you look at the electron total energy, total counts of electron, you typically ionize less amount of high kinetic energy electron compared to low energy. So you typically have, the higher the harmonic order you have a lower efficiency. So there is one more thing to understand, is that when you launch this electron pretty far, on the way back the electron also diffuses, the wave function diffuses. Okay, so therefore when the electron tries to recombine, because of this quantum diffusion, if you like, the amount of if you look at the cross section of the recombining wave function, it becomes smaller and smaller. So when you go to like kilovolt photon energy range, right, the amount of the actual amount of light that you produce is very small. It goes to the to the -6 or -5 or 6. So this is basically the when the electron is going pretty far and coming back, so the wave function diffuses and the recombination becomes less efficient.
Shambhu sir, along the same line, so in gas, like you have some degrees of freedom to phase match the condition and you get this bright harmonic peaks. Do you have like that tunability in solid state, or like are there any degrees of freedom that you can tune and get a particular bright harmonic?
Not yet. So that would be the next big deal.
Okay.
Yeah. Right now, that would be for example, you could maybe take advantage of the birefringence on crystals where there is a different refractive index on two different directions, right? But yes, so far solid state harmonics, they still need to be phase matched.
Okay, yes, that's good. Thank you.
So I think we can conclude our formal session, but we'll keep going with our informal discussion. So please stay with us. Thank you, Shambhu sir, for this wonderful talk, and thank you everyone for joining from Nepal and all over the, maybe we can say, world, because so many people are joining from other place of Asia as well. So thank you, and keep tuning ANPA, and we'll have very soon another program coming. And I would like to conclude today's session, but we will continue our informal session. Thank you.
Thank you so much. From my side, it was an honor to represent attosecond physics community to ANPA and to NPS and to whoever were able to join now. in the platform, as well as looking at us live from Facebook, and those who will be watching this recorded video. Thank you so much.
Yeah, I think I'll ask some questions. Like,